Hi, we're going to talk about circular motion again and apparent weight this time. So, I mentioned this during the lecture on Tuesday, but when a car is turning a corner at a constant speed, it's following a segment of a circle. So, it is circular motion still. So for example, if you think about the exits on the freeway where it's a big curve, that is you're undergoing circular motion when you exit on those. Also, even just going like turning a corner is can also be imagined as circular motion. So we have a car here, it's driving in a circle, um, and our path is shown is a segment of the circle. Um, so one thing we learned on Tuesday is also that in order for there to be circular motion, there needs to be a net force pointing toward the center of the circle. And for a car, that force is the static friction force. So just like how for the actual turning of the tire, it is a static friction force. There's also a static friction force preventing the car from skidding out. So the velocity of the car is tangential to the circular motion, which normally without an additional force, that car is just going to want to continue in a straight line. But the force is needed to change the direction of the velocity, which turns the car. And that force is a static friction force because it's preventing the car from, or the tires from slipping out this way. So we're gonna do a couple examples where we look at cars making turns. But I do want to also mention before we jump into that this isn't just true for cars turning. If a car is going over a hill or down in like a valley, that is also a portion of circular motion. So when it's in that motion, there must be a net force pointing toward the center of the kind of larger circle that you can imagine. So when it's going down, that would be somewhere above the car. When it's going up, it would be somewhere below the hill. And the other thing to think about is what combination of forces gives you a net force pointing in that direction. So let's do this example. I guess I'll read it first. What is the maximum speed with which a 1,500-kilogram car can make a turn around a curve of radius 20 meters on level or unbanked road without sliding? And this is typical for a major city intersection. So when you're just making like a right turn. Okay. So let's imagine, we're looking at the car from behind and it's going around the curve. And this is a car from behind. So then let's draw our free body diagram. But what we're imagining is like the center of the circle is that direction. So we have weight and normal force. Weight, normal force. And then I said the static friction force is the one that points towards the center of the circle. So that's going to point like that. There's our static friction force. Oh, and one thing I forgot to provide here is that the coefficient of static friction, the coefficient of static friction for rubber tires on dry concrete is 1. So, okay. Now the net force in y is 0. No acceleration in y. It's the normal force minus the weight. And then the net force in x is the mass times the acceleration. And this is centripetal acceleration because it is in circular motion. You remember that is v squared over r. So I'm going to write that mv squared over R. And then the only force we have is our static friction force. Okay, cool. So looking back at what we're asked for is the maximum speed. So we need to use this, but we also need a little bit more information about the friction force. But we know static friction maximum is the coefficient times the normal force. And we can take this equation and add the weight to both sides, and we get that the normal force is just equal to the weight. So then let's take this equation and we'll plug in the normal force. mv squared over r equals the static friction force, which is the coefficient of static friction, times the weight, or mg. Okay, now both terms have mass in it, so they can cancel out. Which is good because not all cars have the same mass. So this should work no matter what their mass is. Then we want to multiply the radius on both sides. Oops. Do it like this, times the radius. And then we'll also square root both sides. So we end up with the velocity is equal to the square root of the coefficient of static friction times g times the radius. And then we can plug those in, square root. This coefficient of static friction is just 1. G is 9.8 meters per second squared. And then the radius here is 20 meters. So this is 14 meters per second for the velocity. And yeah, one second. Yeah. So one other thing we can do, because I mean, in general, our lives are, I mean, physics is lived in meters per second, but our lives as people who live in America is lived in miles per hour. So 1 meter per second is 2.24 miles per hour. That's rounding a little bit, but close enough. And so this is about 31 miles per hour. So just so you have something to compare that to, which makes sense. That's either between like 25 and 40 is usually what at least off ramps and things are listed at for recommended speed. So that's where it comes from. Now let's do another example, but this time, well, for one thing, it's a curve on a racetrack. But it's a banked curve, which really just means ours before was flat, and banked means on an incline. So, and when it's on an incline, there doesn't have to be friction for circular motion to happen. And that's what they're asking about, is how fast can they go around this circle without worrying about friction. But the thing with this is we're so used to now with inclines tilting our coordinate axes, but we don't actually want to do that for this one. So apologies, I know that is a little bit confusing, but it is just a special circumstance. So we want to kind of imagine our coordinate axes like that. And what we'll have is the weight force going straight down. And then the normal force is at an angle. Theta, normal force. So, and the main reason for this is because the net force points toward the center of the circle, which is not down the incline. It's like directly kind of horizontal. So I think you would still get a pretty similar answer for the velocity if you tilted it. But if we're being precise, we don't want to tilt it. So then we'll do net force. I suppose first actually we'll write the y component of the normal force and the x component. And we can see that the y component is cosine because it's adjacent to the angle. And the x component is sine because it's opposite the angle. Okay. Now our net forces. Speaking of, I should also write that the net force is pointing this way towards the center of the circle. So net force in y is 0, and it is the y component of the normal force minus the weight. And that's the full weight in this case. And then we have the net force in x. This one is mass times centripetal acceleration, which again is v squared over r. So mv squared over r, because again, it wants the velocity or the speed actually, but so we need to get that in the equation. And then the only force acting in the x direction is the x component of the normal force. So you might look at this and say, well, how in the world do we solve this? There is no equation for a normal force. We just base that off of other forces. But we can use this equation. So we have, if I add the weight to both sides, we have the normal force in y equals the weight, and the normal force in y is the normal force times cosine of theta, and that equals the weight. And then if we just divide both sides by cosine of theta, we get an equation for the normal force. So the normal force is the weight divided by cosine of theta. Okay, so we've solved that. So now we can plug that into this equation. So we have mv squared over r equals the x component of the normal force, which is normal sine theta. So I'm going to instead plug in this for normal. Weight over cosine theta times sine theta. Because remember, this part is the normal force. And then sine of theta divided by cosine of theta is tangent of theta. You could solve this without simplifying that, but I like to simplify. So mv squared over r equals the weight times tangent of theta. And then one more move we can make is mv squared over r, and we'll plug in for the weight, which is just mg, tangent of theta. And again, our masses cancel out, which again is good because cars do not have the same mass. So the structures of what they're driving on should not be dependent on their mass, or at least on any one individual mass. Okay, then we want to multiply both sides by r and take the square root again. This time we get that the velocity equals the square root of gr times tangent of theta. So it's a little bit different, but pretty similar to the equation from the last example. And then we'll plug things in. 9.8 meters per second squared times 70 meters times tangent of 15 degrees. So this one, we get an actually a little bit smaller velocity of 13.6 meters per second, which 13.6 times 2.24 gives us about 30 miles per hour. About 30 miles per hour. So interesting to see that it turns out to be the same, even though the radius of the circle is different. So it might be beneficial to also have a component of friction in going around a corner. So those are those examples. Let's go back to the slides for a little bit. Okay, now I want to talk about apparent weight. So in general, the apparent weight is just the magnitude of supporting contact forces, which sounds weird, I know. But it really is actually just the normal force, because the normal force is kind of the force you feel that's holding you up. And if multiple forces are contributing to that, you can end up feeling heavier or lighter than you actually are. So we have an example here of a man in an elevator. The elevator is accelerating upward, and the man feels heavier than normal. If we look at the free body diagram, we have the weight force that stays the same because we're talking about apparent weight or what it feels like. But the normal force is bigger because we have a net force pointing up because it's accelerating up. And in order for that to happen, either we have to have an additional force or it's just that our normal force is bigger, which also makes sense if you can kind of think of the elevator being pulled up and you're being pulled up by the elevator, like by the floor of the elevator. So, if we, and apologies for making you imagine this and not having it on the slide, the net force is equal to the normal force minus the weight, and net force is mass times acceleration. And to find the apparent weight, we want to solve that equation for the weight. And what we end up with is we want to solve for the normal force or the apparent weight. So what we end up with in this case, and we'll do an example with this to make it more clear if it's hard for you to follow the kind of algebra without seeing it, which I totally understand. But we end up with it being the weight plus the mass times acceleration. So that is why he feels heavier, because on top of his weight normally, he also feels this big normal force pushing him up and making him feel heavier. So you've most likely experienced this similar situation, less dramatically maybe, in a car. Oh, actually, dramatic, I don't know. Maybe you played corners as a kid and shoved into the person next to you when you were going around a corner. But what happens is you feel like you are almost being pulled to the outside. And what that really is just, again, that idea of you have a velocity that's perpendicular to the circular motion. And in general, like an object in motion wants to continue with the motion it has, unless there's a force acting on it that changes that in some way. In this case, it just changes the direction. But what is it that you feel in like the car, for example? So it depends a little bit on like how close you are to the side door. If you really are kind of thrown into the door, then it's the normal force from the door. If you're well strapped into your seatbelt, that might be what is kind of forcing you to turn as well. And it acts the same way as the static friction force does for the tire. It causes it to turn or change direction instead of just going off. But what you feel, like the thing that feels like a force that is making you slam into the person sitting next to you or the door or something, is really just your velocity wanting to continue on the way it was and being forced to turn. And I know that might not seem directly connected to apparent weight, but it is, again, the contact force. So now let's bring it back to more explicitly apparent weight. So let's think about this roller coaster specifically. So this picture is called Fireball, but the one I'm familiar with at Wild Waves and Federal Way is the Ring of Fire. So it's just like a roller coaster going around in a circle. I've never gone on it because that's not my thing. But let's take a look at the forces at the top and bottom of this roller coaster. Okay. So let's start with the top. At the top. And we'll just draw the free body diagram. So we have our weight force. And then there's also the normal force from the surface. Although, I mean, maybe you're barely touching the surface, but it's still there. Maybe we'll make it smaller. And then this is circular motion, so our net force needs to point toward the center of the circle, which is down, F net. And then we can do our sum of force equations to find the apparent weight. Or I guess we're just doing one equation because we're only looking in y. So F net y equals, and it's not 0, it's mass times that centripetal acceleration. But that's pointing down, so it's going to be negative a. I'm going to give it a subscript c for this, so that we remember that's what force it is, or acceleration it is. And then both forces are pointing down, so they're both negative, normal and weight. And now we can cancel out all of those negatives. So we put them in there in the first place because it's good practice to keep track of how signs work in free body diagrams and force equations. But since they're all the same, it cancels out. And so we have mass times the centripetal acceleration equals the normal force plus the weight. And then if we solve for the normal force, we can find the apparent weight, because remember, that's what it is. So if we just subtract the weight on both sides, we get that the normal force is mass times acceleration, centripetal acceleration, minus the weight. And we could plug in a little bit more. For example, if we know the velocity, we could say this is v squared over r minus mg. If you want to give all of those, like, as kind of complete as we can. And this is the apparent weight. So at the top of the roller coaster, the person is going to feel less heavy than they actually are, because this normal force is less than their weight. We're subtracting their weight from the acceleration. That's going to be smaller than their weight. So the normal force, or the apparent weight, is less than their weight at this point. Then we look at the bottom of the roller coaster instead, at the bottom. So we have our weight force going down, but this time our normal force is pointing up, and the net force also needs to be is pointing up, because that's where the center of the circle is. So the normal force needs to be bigger than the weight. You might be able to already guess that the normal force, the weight, apparent weight, is going to be bigger than the actual weight. But let's prove that. So again, net force is pointing up. We have net force in y is mass times the centripetal acceleration. This time it's positive because it's up. And then we have the normal force minus the weight. And then, again, if we solve for the normal force by adding the weight to both sides, we see that the normal force is the mass times centripetal acceleration plus the weight. And that is mv squared over r plus mg, for example. And we'll say this is the apparent weight. So the normal force, or the apparent weight, in this case, is bigger than the actual weight. And one important thing with this is this example, especially just in general, apparent weight really shows the importance of not trying to get to this step without doing this step ahead of it. Because you could look at that and say, why does my net force plus the weight equal this? And that's because when you rearrange the equation, that's how it works out. Because initially the weight is subtracted from the normal force. But if you don't do the previous step, it just doesn't make sense. So that's also a good reason why I push for practicing free body diagrams. Okay, last point on this is there is a point at the top. There's a point where the net force is just equal to the weight, so the normal force is equal to 0, and so is the apparent weight. So you kind of feel like you're in free fall, which you are, because that's what free fall is. It is when the net force is just the weight. So let's look at that situation. Weight, net force, and then net force in y is mass times negative centripetal acceleration, because again, still pointing down, and that equals the negative weight. those negatives cancel. And I'm going to plug in v squared over r for the centripetal acceleration. So we get m v squared over r, and then I'm going to plug in the equation for weight, so just mg. So our masses cancel, and then we can solve for this velocity here. Because again, we feel like we're floating, or really I think you would feel like you're falling, kind of. But so there is no apparent weight, but there's another thing we can see, which is how fast you need to be going so that you don't actually fall and instead you continue the circle. So that's just the square root of the acceleration due to gravity times the radius of the circle. And this is called the critical speed. Critical speed, which is the minimum speed you need to complete that circular motion. So don't freak out if you're, riding the Ring of Fire or some other thing like this, and you feel that sort of free fall moment. I mean, you might want to make sure that it's going at the right speed, but for the most part, we should assume that if the manufacturers are still in business, they have made sure that you're moving at the right speed to not fall out. Okay, there's just a few more slides now. Okay, it's just the definition of critical speed really quick. Again, the minimum speed needed to complete that circular motion. Now I want to just briefly talk a little bit about orbital motion. So if we kind of think about like a high tower or something and an object being launched out of it, if we launch it with a certain speed, it does something like this example A, which is mainly just projectile motion. We give it more initial velocity, the ground, because of the curvature of the planet, starts to curve away from the projectile as it's falling. But then, again, if we continue to increase the speed, it is again falling away, so that it actually lands at an even further point. But eventually you can get it going fast enough that it ends up just falling all the way around the planet, and in turn actually just orbiting the planet. And this is an example of free fall, just like what you feel at the top of the roller coaster sometimes. And it's free fall because the only force is gravity. It's not that there are no forces, and you don't feel weightless because there is no weight. You feel weightless because there is no normal force holding you up. So in orbital motion, just like with projectile motion, when an object, like throughout its entire trajectory, the weight, force, and acceleration due to gravity is directed down the whole time toward the kind of center of the planet. The same thing is true as when we zoom out toward orbital motion. The net force is always going to point toward the center of the planet. So it doesn't matter where in the orbit the projectile is, its net force and weight force is going to be pointing toward the center, just like here. So orbital motion acts just like circular motion. And we can even use the same relationship with the net force equaling mass times the centripetal acceleration, or mv squared over r. And another point, so if we look at one of these examples where an object is in free fall in orbital motion, we just have the weight force, and that means that the net force is equal to the weight force. So mass times acceleration equals mass times gravity. Centripetal acceleration is v squared over r. So we get that the orbital velocity, because that's what the velocity would be of orbital motion, the orbital velocity squared divided by r is equal to the free fall acceleration. There we go. And then if we solve for that velocity, we get the same thing we just got, which is the square root of g times r. So again, what we end up with is the critical velocity. So critical velocity works in a variety of circular motion, either, a roller coaster or um, in an orbit around a planet. And then just really quickly, I want to introduce Newton's law of gravitation, which is kind of a larger scale version of our weight force, which is mass times acceleration due to gravity. But if we have two planets or two massive bodies of any kind at a distance r apart, the force between them is g, which is the gravitational constant, which is just a universal constant, and it's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Anyway, g constant times the mass of one times the mass of the other divided by the distance between them squared. And so this is the force that each one enacts on the other. And this is an example of an action-reaction pair of forces. Because, for example, here, this is the force that planet 2 enacts on planet 1. And this one is the force of planet 1 on planet 2. And you can see they're equal in magnitude and opposite in direction. And we'll talk more about this later, but I wanted to introduce it here. And that's everything for now.